Hey class, this is lesson 7.7. Our objective here is to learn how to model exponential growth and decay. Go ahead and do the vocab quick. All right, so we're going to learn about exponential growth and decay. If you're looking at a graph, check this out. You can tell a growth graph, it's a curve that goes up, and it usually gets stuck in one spot, in this case really close to zero, and then it just continues to rise really fast. Decay is kind of the flip of that. Looks like this, starts up high and comes down, and it keeps getting closer and closer to zero. You can tell a growth function by its equation if the base is greater than 1. And you can tell a decay function if the base is less than 1. Now remember that earlier we defined exponential as b had to be not equal to 1 and greater than 0. And then a is our initial amount. That can't equal to 0, must be greater than 0. And these are what the graphs look like. All right? Growth factors are numbers you can multiply by that make the numbers keep going up. The numbers you would multiply by are numbers that are greater than 1. So growth factors, 3 could be a growth factor, 1.05 could be a growth factor. If you multiply by numbers that are less than 1, then the numbers are going to go down. Decay factor are numbers that you multiply by that will make the numbers get smaller, and that could be numbers like 1/2 and 0.93. You might think of point as 85% as a decay factor, because if you take 85% of something, it's always going to be less than what you started with. But in fact, a percent isn't a decay factor. If you change it to the decimal value, then now it's a decay factor. And more specifically, if we're losing 15%, then we would use that decay factor. All right, so let's do some problems with growth, exponential growth and decay. Suppose the population of deer in a region was 3,500 in the year 2000. Since then, the population has grown by 3.5% annually. What will be the approximate population in the year 2020? To find the growth factor that you need, write this down. What you're going to do is take 1, then add your rate divided by 100. And the reason you do that is so you change your percent into a decimal. So what I end up with is 1 plus 0.035. So, and you'll probably be able to do that in your head, just move the decimal over 2 places to get that number. So, and then I'll just simplify that, that's 1.035. If I multiply by 1.035, my number is going to grow by 3.5%. I'm always going to have 3.5% more. So, what I'm going to do is my population of deer, my initial population is 3,500. Then if I multiply by 1.035, and then I need to multiply by that number as many times as the number of years that this population is growing. Since we're going from the year 2000 to the year 2020, that would be 20 years. So I'm going to do this to the 20th power. So if I multiply that, I need a calculator for that one. I get 6,964 and then some decimals. But since I'm talking about a population, I think it makes sense to round to the nearest whole here. So I'm going to say 6,964. All right, go ahead, you try that. I'll help you fill this in, and then you can fill in the rest there with some definitions here. It says fill in the words in here. The exponent here is 25, so we'll put exponent there. Actually, you go ahead and try and figure out which goes where. And if you multiply this out now on your calculator, you're going to put in 25,000 times 1.015, and then you have to use the caret key, which looks like this to get the power. And you should get this number, 36273.63, and I think there's some more decimals. But since, again, we're talking about a population, we're just going to round that to the nearest whole. So 36,274 makes sense. Okay, another form of exponential growth given as a formula here is the formula for finding the amount of money in an account that earns compound interest. And it works like this. You have the principal or initial amount, just like we had the initial population. You make a growth factor. It's a little more complicated here, but R is just your percent, like we had before, written as a decimal. N is the number of times that it's compounded. So some things are compounded quarterly. If it's compounded yearly, then that N right there is just 1. But if it's a smaller time, then it's whatever portion of year. It could be monthly, in which N would be 12, because there's 12 months in a year. Could be quarterly, which means every 3 months. So that N would be 4, and so on. All right, so here's some examples of using that, and I'll just try and describe some of these. So our principal here in this one, in other words, how much money we have in the account is $1,200. Our interest rate here is 4.5%, and you can see that in this number right there. It's divided by 12, which means we're figuring out that interest 12 times a year, so it's monthly. And up here is 12 also, which means we're doing it for 12 months or 1 year. So this is going to give us the value in an account that earns 4.5% interest in 1 year, 1 year's worth. And if you multiply that out, and you can do it a couple ways, but one way you could do it is just simplify the part inside the parentheses. Just do 1 plus 0.045 divided by 12, and that gives you 1.00375. And then we have to do that to the 12th power for 1 year. And if you do that, you should get $1,255.13. Here we're going to round to the nearest cent since we're talking about money. Now, I'll explain these other two to you, and I think you can go ahead and figure out what the values are. But so our principal here is $500. That's how much we have in the account. This interest rate, if you move the decimal 2 places to the right, that tells us we have 1.5% interest. We're dividing by 4, so that means we're doing this 4 times a year. So this is a quarterly compounded. All right, and we're doing 4 quarters would be 1 year, but we're doing that times 5. So this is actually 5 years worth of interest here. So simplifying all that, if you want, you could put the growth factor all as one number by simplifying it, and you get 0.00375. Interesting that that's the same number as the last time. And then we need to do that to the 20th power. And you can try to do that. Okay. This last one, we have $15,000 in the account. The interest rate is 2%. We're doing it 6 times, which means semi-monthly, 2 months, every 2 months. 6 times to the 6th power would be 1 year, but we're doing it times 10, so that means we're doing 10 years worth here. So let's try some of those. So Michelle invests $8,000 in a money market account that pays 3.25% interest compounded monthly. How much will there be in the account after 12 years? So our amount is equal to P times the quantity 1 plus the rate divided by the number of times, and then we have to raise that to n for 1 year, and then times t being the number of years we're doing this. So in this case, we're going to do p, which is 8,000, initial amount. 1 plus our rate is 3.25%. We're going to move that over 2 places to get the decimal. 0.0325. Divide that by compounded monthly, so that there's 12 compounding periods in a year. And for 1 year, we're going to do to the 12th power. But we want it for 12 years, so we have to do times 12 to get that answer. And if we simplify that, and what I would suggest you do is do this part in your calculator first. Then raise it to this number, which is 144. Then multiply it by 8,000. If you do it in that order, you don't have to worry about the parentheses in the order of operation. So if you do all that and try it and do this on your calculator until you get this answer, you should get $11,809.62 if you round to the nearest dollar or cent. All right? Okay. So go ahead and do this problem, and you can check back and see if you're doing it right. All right. We're going to do some decay now. Decay is a lot like growth, but to find a decay factor, we, instead of adding to 1, we're going to subtract from 1, because you need to multiply by a number that's less than 1 to make things go down. So to find our decay factor, we're going to do this. We're going to take 1 minus our rate. And our rate needs to be written as a decimal, so we're going to move that over 2 places, so 0.029. And then I'm going to go ahead and simplify that. That comes 0.971. And then the rest is pretty much the same. Take your initial population, which is 148,220. And then we're going to multiply by, so times, our decay factor, this case. And then we're going to raise it to the number of years we want to do it. And we want to go from 2005 to 2015, so that's 10 years. Okay? And if you do that right and multiply it out, you should get about 110,433 if you want to round it to the nearest whole number. All right. So go ahead and try that. See if you can get it right. All right, I hope that worked out for you. One more thing. Do the lesson check here. How can you simplify the compound interest formula when the interest is compounded annually? Explain. Well, one thing about our value of n, if it's yearly, is 1. So if we simplify that, we can put a 1 there and a 1 there. And what we end up with is p times 1 plus r divided by 1, and 1 times t, and r divided by 1 is just r, and 1 times t is just t, so we get a much simpler formula. We can just do it. And this looks a lot like what we would do with any exponential growth problem. And in fact, our exponential decay would be our initial amount if our money was losing, and instead of 1 plus r, we would do 1 minus r to the t. So that would be decay. And this one is growth. All right, that's it. I'll see you tomorrow.